Okay, today we're going to cover 3 topics. Hopefully we'll get through all these. If not, we'll finish up the last one next time too. But the idea is we want to cover 3 different things. We're going to finish up talking about power flow, which is essentially given certain conditions, given certain demands, certain productions from generators, how does power actually distribute itself over a network? Which way does current flow? What nodes have what voltages, etc. So we'll finish that up. Then we'll talk about a slight twist on this, which is called optimal power flow. And in optimal power flow, the things like the generation for each generator is no longer a fixed quantity. So we're actually now solving an optimization problem, say to minimize the cost of generation or maybe to minimize something like the carbon emissions of generation. We're solving this optimization problem subject to the constraint that the solution still has to obey power flow. So unlike before, I guess we had a little bit of fuzziness because the slack generator could generate more or less power. But now in optimal power flow, typically, a lot of generators can generate different amounts of power. And the question is, how do we best allocate these generators in order to optimize some objective? And then finally, we'll talk about an instantiation of optimal power flow. You can think of it in some ways. But this is power markets. And it's uses optimal power flow, but it actually encompasses a lot more as well. And this is going to be a very high-level introduction to power markets. There are entire courses on power markets, so we're going to cover this very, very fast. But I want to give some idea about the complexities involved when you start having a non-centralized or non-monopolistic market for power, we'll say. It's still centralized in some sense, but it's not a setting where one entity controls all the actual generation. If you have multiple different companies controlling different generators, how does that actually bear itself out? How do you do this? And how do you use optimal power flow to actually coordinate these markets? So we'll cover that. Before I get started, though, just some administrative details. Everyone should have. I sent out comments on all the projects this morning, so hopefully everyone got those. If you didn't, then come talk to me, because I did send them all out. I maybe just missed you on your email. And the homework, as I said in the email, was due next time, Thursday, at the beginning of class. Remember, this time I'm going to be strict about it, where if you don't get it at the beginning of class, it will count for late day, even if you turn it in at the end of class. If you come in like 5 minutes late, that's okay, but if you don't come to class because of it, then it'll count for the late day. And then also the little makeup lecture, which we'll have, I'll post online. I'll post it sometime the next day or 2. It'll cover sort of a pretty self-contained unit on some simple power electronics, and you can watch that whenever it is. We are going to do, there is one question on the next homework that has to do with power electronics, but you can hopefully get most of this on your own. It's sort of somewhat separate from the rest of this. That's why I actually wanted to do this, keep doing this in class versus doing this part is on the lecture and then the other part in class. So I'll post that shortly. Are there any questions from last time? Okay, so let's jump back into power flow. And if you remember from last time, I was setting this up in a way where typically when you see power flow, you'll write out these equations kind of in terms of the explicit sines and cosines. You'll take Jacobians with respect to each of these different quantities explicitly, and that creates a bunch of kind of big complicated equations. And this is just, I'm not deriving these equations right here, so it's somewhat, you have to take my word for it, but they do follow from pretty simple matrix calculus. And it actually gives you an expression. If you treat power flow in its vector form, you can actually come up with very simple forms for the Jacobian of all the necessary quantities, and that makes these sort of computations a lot easier in practice. So from a high level, what we're doing here is we're taking all the quantities we care about and putting them to a big vector, which I'll call z. So z is going to be, I'll just write it up here again, z is equal to the vector of all the thetas, the vector of all the v hats, which are the voltage magnitudes, all the p's, real powers, and all the q's, the reactive powers. And it's important to know that this is a vector in r to the 4n, where n is the number of nodes in our network, right? So remember, half of these things are going to be known. Okay, so I'm writing this vector in terms of all the things that might be unknown, but half of them actually will be known, right? Because we know, for example, the power and the reactive power at loads. We know the and et cetera, we had in the previous slide. So only two n of these are known. And in the next slide, I'll actually talk about the index set I being the set of indices of all the things that we don't know. So just to preface what we're going to do in a second, you'll see that in the next slide. Then we define this function g of z, and g of z is essentially the residual of our power flow equations. So remember, power flow says that v, or rather s, which is the complex power, equals v times y bar v bar. Sorry, diag v. S equals diag v y bar v bar. That's what it says, right? But what we want to do in our equations here is deal only with real quantities. We could, solve power flow in terms of its actual complex equations, but the difficulty with that, as I said before, is that things like voltage are a little trickier, where you don't easily know the real or complex part, which knows the magnitude and the phase angle. So it's easier to treat everything in terms of real quantities. Z is nothing but real quantities. And we want to do the same thing for G. So what we do just very explicitly is we make G both the real and imaginary residual of our power flow equations. So G is essentially the difference between these two things. It's diag v, and by the way, v here would of course be, in this case, v would be something like diag v hat times e to the j theta, where this is seen to be assumed to be done element by element. So you take all your thetas, exponentiate them, and multiply them by all your v hats. That's just writing out v in terms of these quantities here. So this G would be something like diag v times y bar v bar minus s. But this has a real and imaginary component. So really it's just going to be, the first bit's going to be the real component of that, and the second part's going to be the imaginary component of that. All right, so that's just how we're defining G. And G is going to be a function that takes as input vectors in 4n and produces vectors in 2n. Therefore, the Jacobian of G is going to be, so the Jacobian dz of G is going to be equal to well, first not equal to anything, but it's going to be a matrix. Remember, the Jacobian has dimensions this guy by this guy. This is going to be a matrix in 2 to the n by 4 to the n, where each element, this element here, this block here, is essentially the Jacobian of that thing with respect to theta. This is the Jacobian of that first element with respect to v, etc. And for example, these ones over here are really easy, right? Because this term, these equations here just have a negative p effectively and a negative q. So the Jacobian of this block here with respect to p and q is just a negative identity. It's just sort of almost, you'd actually probably never even see that one written in most textbooks, but I just want to kind of make it clear that what really is happening here is that you have a 2n by 4n Jacobian. These terms are kind of the interesting ones. It's the derivatives with respect to the different phase angles and voltage magnitudes of the objective. And then the other one here is just kind of the obvious ones. So, and they have a very simple form, essentially Jacobian. I'm not going to prove it, but if you form two matrices, J1 and J2, defined by these things. These are both complex matrices. They're using the actual complex. They have, a J term, and they have some complex quantities here. And if you just form these two, though, and take the real and imaginary components, that gives you the Jacobians of the different power flow equations. And that's going to be, by the way, much faster in MATLAB, say, than trying to do a for loop and compute all of those Jacobians of the different types manually. The other nice thing that I've mentioned is that J1 and J2, if you just look at these equations, what you'll see is they actually have the same sparsity pattern as y. So if y is 0, has a 0 entry, remember a 0 entry in y corresponds to there being no transmission line between nodes I and j. And these things will have zeros in those same locations, which is very nice because it means we can exploit what are called sparse solvers, basically methods that exploit the fact that there's a lot of zeros in a matrix to solve these things more efficiently. That's very nice in practice. OK, so now just to finish up how we actually do this. Remember, we know of this vector here, we know 2 to the n elements. Sorry, not 2 to the n. We know 2n elements. And we don't know the other 2n elements. And the goal of PowerFlow essentially is, given those 2n known elements, find the other 2n elements such that this equation is equal to 0. G is equal to 0. So that's really easy to do, actually, using this notation and Newton's method. What we do is we just take, and I'll erase some of these things. I'm going to call the Jacobian also J from the previous slide. That's the Jacobian that we were defining in the previous slide. So all that we do is we take zi, which are the unknown elements of z. And by the way, in MATLAB, you could just write that as, zi. That would be fine to write it like that. That would just, so if I is your index set of all your unknown elements, then zi in MATLAB would give you the things that you don't know. And so what we do is we just take zi and set it to be equal to, well, the previous zi minus the Jacobian inverse. But remember, the Jacobian here is a 2n by 4n matrix. So it's not a square matrix. So you can't invert a non-square matrix. But we don't really want to invert the whole matrix. What we want to invert is just those elements corresponding to the things that we don't know about. Those are the things we're actually changing. We're not changing anything else. So what we do is we take, and I'll use kind of MATLAB-esque notation here, we take all the rows of J, but only those columns corresponding to the things that we don't know about, invert that, and multiply it by G. G is this whole thing, so G is a vector in 2n. So first of all, the sizes all add up, right? Because this Z sub I is a vector in 2n, minus a matrix, which is 2n by 2n, times another vector in 2n. And so this is just, hopefully you can convince yourself, but this is just Newton's method applied to finding those elements in Z that we don't already know from the beginning, is all that we're doing here. Now, one important point is that Newton's method is not guaranteed to converge in all cases. This is sort of a problem I mentioned a little bit before. You can have cases where Newton's method will start making bigger and bigger changes. This has caused all sorts of problems. To get rid of it in some cases, what you can do is not take a full step, but actually add a scaling factor here for some alpha less than 1. You won't have to do that in the homework assignment or anything like that. You won't have to do any of that in things we see, because typically, actually, if you start at a reasonable solution, like say V is all just sort of the nominal voltage with 0 voltage angle, then these things work out pretty well, but doesn't always converge. The other thing is that, well, we know it doesn't always converge because there isn't always even a solution. You can easily come up with cases where there is no set of powers that will solve these equations. They're nonlinear equations. Essentially, if the powers are just too high and you can't accomplish it with any sort of reasonable voltages or extra power for the slack generator, there are plenty of times where you can't solve this. So we won't worry about that. The cases we'll see, they will be solvable with a simple update here. And the reality is that a lot of kind of reasonable cases of power flow are solvable just doing this. And it works sort of amazingly well in practice. Oh, actually, I had a few more technical comments first. First of all, when you see power flow, you'll often see something called PUs. So you'll see things reported. It's talking about voltage. Voltage should be in kilovolts or many different units. I mean, depending on the scale of the things, it could be 100 kilovolts or 500 kilovolts, or it could be, if it's a smaller system, it could be 10 kilovolts, something like that. Or distribution, it can be even lower. But typically, the actual voltage and the actual powers don't matter that much. What matters is kind of the relative powers and the relative voltages involved in the power flow solution. So what you'll often see is that voltages are scaled to what are called per unit quantities. They're abbreviated by PU. And what this does effectively is it assumes some nominal voltage is equal to 1. Usually the voltage, say, at the slack bus is equal to 1. And then sets everything else relative to that. So rather than saying this generator has 485 kilovolts, you say it has some number of PUs, like 0.95 PUs or something like that. It's just a sort of a scaling thing. And by the way, it also makes Newton's method a little bit nicer if you're working with quantities that are all kind of reasonably scaled. We do the same thing with power. So power is you typically don't do per unit stuff because the actual power does sometimes matter. I mean, voltage is sort of, it doesn't really matter how voltage it is. It can be stepped up or stepped down depending on the transformers. But power actually does matter. I mean, power is sort of what you're paying for. So power is kind of more natural to have actual units of megawatts. But at the same time, you don't want quantities like, a million in your numerical solutions. So typically, we scale all the quantities by a quantity called the base megavolt amperes, so base MVA. And most power flow files will actually tell you what the base MVA is and then give you power quantities that are all in relation to that. So you scale voltage by these PUs and you scale power by this base VMA. You might see power is also sometimes called PU when you scale it by this, but this is sort of a simple point. All I'm saying here is that in real power flow, you will see these things all scaled to a certain amount, so that just be aware of that. You're not talking about raw, absolute megawatts or absolute kilovolts or whatever. Okay, so now let's look at a simple example of a power flow problem. So here is a presentation of the things that we know. This is, remember, a bus diagram. So each of these things, this is a bus bar. These are transmission lines there. This is a load. Those are generators. And the things I'm drawing here are the things that we know in our power flow problem. So at the slack bus, the slack generator there, we know the voltage is 1 PU at a voltage angle of 0. Because we fixed that to be our slack generator. We don't know how much power it produces because that's going to be adjusted depending on how we need to make up losses in the network. But we know that it has voltage magnitude 1 and 0 power angle. At the PV generators, this is another generator that's not the slack generator. And at these generators, we know how much power they produce, the real power. So in this case, it's 0.5. I think these are all scaled to megawatts here, but it doesn't really matter. I could scale into whatever I want. And the voltage magnitude is 1. So those two things we know. We know P and we know V magnitude. And so that's what we know there. And finally, at the load, we know the real and reactive power. And it's important these are negative quantities because this is a load. So load by convention has negative power. We also finally know the resistance and reactance of all the different transmission lines, which we're going to use to form that Y matrix. So this is just a quick sort of plot of our power flow problem. This is what we know. This is the input to our problem. What we don't know are the things at these loads, the other elements of these loads. So here we don't know the voltage and voltage angle. We don't know there the reactive power or the voltage angle, and we don't know there the real and reactive power. And here are, when you run power flow and run Newton's method, I'll show you sort of a graph of how Newton's method converges in a second. But when you take this as input, these things are all as input to your power flow problem, and just run Newton's method on essentially the other variables, what you'll get is this. So the actual numbers here aren't really important, but what is important is that essentially what we're doing is we are determining the other quantities from the known ones. So for example, at the load, we determine, to satisfy these equations, that the voltage has to be 0.9 PUs at negative 12.95 degrees. And then similarly for the other generators, for the other generator, and then we determine the power that the slack bus generates. Okay, oh, and by the way, if we also want to know, for example, the currents flowing over the lines, now it's easy, right? Because now we know the voltage at the two endpoints, just apply Ohm's law, and we get the current flowing over the line. Okay, so that's sort of just a simple numerical example. You'll actually run these on your homework, or the next homework too, which will be out on Thursday. You will run these as well. So you'll implement power flow, and you'll run the equations to get some solutions for different size buses. Bigger ones than different size networks. Bigger ones than this, though. Okay, so what I want to show now is just the progress of Newton's method. So remember, the nice thing about Newton's method is it has what's called quadratic convergence. And what this means is, when you're close enough to the solution, and by close enough, that's sort of a very vague term there. You have to just sort of, it's different for each problem. But when you're close enough, whatever that means, the number of bits of precision you have in your answer will double at every time step. And that's a pretty impressive sort of increase in accuracy every time. And so what this looks like in a graph, and we saw the same thing actually for Newton's method for solving the loss function, the logistic loss function, right? When we use that to solve logistic regression in the machine learning problem. But here we're showing the norm of G as a function of number of iterations of Newton's method. And remember, G is this thing. G is the thing that we're trying to drive to 0. Because when it's 0, that means we satisfy power flow. So I'm showing the norm of G versus iteration number. And what you see is that very quickly, this starts going to essentially numerical precision on a PC. I mean, you can't get any better than this unless you start using variable precision numbers and stuff like this. So after 6 iterations, it's already gone from some initial guess, which is not at all the correct solution, to essentially the exact solution in 6 iterations. That's pretty cool. What's really cool, though, is that the same pattern holds almost, not quite, but in practice, almost independent of the number of nodes in a network. So this is kind of cool here because it's a 3-bus example. It's a sort of little toy example I just cooked up here. It might not be that impressive if you can solve this. This next graph here shows the same thing on an IEEE 300-bus example. The IEEE in the 90s or 80s even published a bunch of these test cases of power systems. The systems actually were from the 60s and around then, but essentially these are sort of standardized cases people use to evaluate power flow methods. And this is a 300-bus example. It's a real power system. So this is sort of non-trivial, right? I mean, 300 buses is a pretty reasonably sized system. And again, at our 6 iterations, we get something that's maybe not quite. We were here before, but then you run one more iteration, maybe 7, and you're at numerical precision. Actually, typically don't go that much below 10, just because you can't hit things like round-off error in double precision. So. Again, after 6 iterations, you're essentially to what a computer can compute. So that's pretty impressive. Doesn't really matter. I mean, this looks exactly the same as this one here, effectively. And it's a 100 times bigger system. So this is sort of what's nice about Newton's method. It works very well, almost independent of the size of the network. That's not quite true, but in practice, it is often almost true. All right, so just some quick comments. There are many extensions to Newton's method that people do that can speed things up a little bit. These were really sort of a big deal maybe 20 years ago when little speed ups in computation could mean a lot to us. Here, at this point, I'm less convinced they're that important to know. They're good to know about, but I'm less convinced as a practical tool that they're really that useful. What they do essentially is that they take steps, essentially. So basically our update here says we have zi, we set it to be zi minus some update here. And you can actually make other updates that are a little different from this that still provably will converge to the solution. And the trade-offs involved usually are we trade off the number of steps you need for convergence. So you need more iterations to converge to the optimal solution. But each computation here might be a little bit cheaper than, say, inverting the entire Jacobian. Because that can still be a big thing. I mean, it's sparse, so it's nice. You can use sort of nice solution methods for it. But still could take a while So you can use other methods instead. And there are things like fast decoupled power flow that essentially takes two blocks of Jacobian and ignores them and only looks at the blocks on the diagonal elements because they're usually bigger in size. There are also a lot of other similar things like that where you essentially approximate this inverse rather than form it exactly, or you approximate this linear system here, this linear solve here rather than doing it exactly, and that can speed things up sometimes, get you a better solution, or maybe it gets you, an initial solution quicker or something like that. Even if you don't get to the super high accuracy as fast as Newton's method. For what we're doing in this class, Newton's method is fine. It works really well. This on a 300 exam, this should number of iterations versus the thing, versus accuracy. What I'm, of course, not showing is it does take longer to solve each iteration here because you're solving a 300 by 300, or rather 600 by 600 system here, because there's 2n variables that are unknown for each bus. So that definitely takes longer per iteration than this guy here. But it still is like less than a second easily on your computer to solve it. If you guys are used to solving those homework problems where you have to wait minutes to get a solution, this is seconds now. So you'll be a little happier maybe on this next homework. And finally, just the solution is not guaranteed to exist in general. Both because Newton's method might fail to find it, but then the point here is that it could just fail to exist, period. So that can be a bad thing. Now, one simplification to this power flow, which is called AC power flow, because it's finding the full power flow solution for an AC system. One simplification to this is called DC power flow. And this actually is quite important as a simplification because it has some nice properties that AC power flow does not have. So I think actually this is a very nice simplification that's very important to know about, and you'll work a little bit about this with this on your homework. One point that I do want to make though is that DC power flow is a horrible name for what this is. DC power flow makes you think they're DC power, right? And it has nothing to do with DC systems. It's not anything about direct current systems. What it really should be called is approximate linear power flow or something like this. What we do is and so it's not power flow computation for a DC network. It is a linear approximation to AC power flow. And so you simplify these equations. So the real problem with this power flow equation here, right, is that it's nonlinear in V. So we can't just solve it with matrix inverse anymore. We have to break out all these other methods like Newton's method, and there may be issues like there's no solution, etc. So what DC power flow is a linear approximation to this system, to the AC system. You ignore certain terms, you keep other terms, and you get an approximation to this full power flow equation in the AC case, but as a linear system. So first of all, a few assumptions. You first of all assume that all line resistances are 0. This sounds crazy, but the reality is that the reactance of lines, the complex part of impedance, is typically much bigger in magnitude than the resistance for big transmission lines. Just essentially their inductive element is much bigger. Their inductance is much bigger than their resistance. Well, inductance scaled by the appropriate things is much bigger than the resistance. And so actually inductance is typically what drives how power flows in a big network, in a transmission network. So it sounds like a crazy assumption, but it's not horrible actually. The second thing we're going to assume is that all voltage magnitudes are equal to 1 pu. So we're not going to have voltage vary at the different nodes. It does vary, but again, maybe it varies by small amounts. If you have one voltage that is like 1 pu and which is like 0.1 pus, that actually will typically not have a power flow solution, and so you're outside the range of the feasible range. Anyway, you have voltage collapse, and your network would actually physically be down. So in most operating systems, this is a reasonable, if not completely correct assumption. They're more like 0.9, 0.8 maybe if it's really bad. So calling all 1 may be okay. And then finally, we'll assume that all voltage angles are small. That's the differences between theta I and theta j at 2 different nodes. And so we'll assume then that we can approximate these voltage angles with small angle approximations. So the sine of theta I minus theta k is equal to just theta I minus theta k. The sine looks like a linear function around 0. And similarly, the cosine of this thing is equal to 1. And this holds true for all I and k. So we assume it's true for all different pairs. And for sort of an absolute, and for the absolute sine of theta I equals also theta I, because we assume they're all also close to 0, because the slack bus actually is the one at 0. OK, so that's sort of the assumptions we make. And then if we make these assumptions, which you can show, and you will show this on the next homework, is that you can simplify power flow to be, this equation essentially simplifies to say that P equals negative B theta, where B is the imaginary part of the admittance matrix. So you can show that this is what falls out of it, and that Q, the reactive power, is always equal to 0. This is not actually immediately completely obvious that those assumptions tell you this, but they do, and you'll prove that on the next homework. And now finally, given a solution to DC power flow, we can again determine the current that flows along any line by just Ohm's law. Ohm's law just says that, well, we take the voltage at the current flowing from node 1 to node 2 equals the voltage at node 1 minus the voltage at node 2 times J of this thing. And if you plug in, this actually has the voltage, of course, has magnitude 1, has phase angle, whatever the thing was, but then we make the small angle assumption again, and so what falls out actually is that you just have theta 1 minus theta 2 over the reactance of the line. And so that also equals, by the way, this matrix B, 1, 2 times this thing. So it's very easy, given the solution to DC power flow, just like with AC power flow, to compute the currents flowing over the lines. And the really nice thing here is that we're back to having a linear set of equations. This is now, once again, linear. And so we can just use a linear solver to do it. And then probably actually more importantly, looking forward, we can more easily include terms like this in an optimization problem. So if we're actually optimizing over different powers according to some objective, doing that, including a general nonlinear constraint, can be nasty. We will do that still. We'll do the nasty version. But this version can be much easier in practice. So people often do that because for large-scale grids, this is not actually all that good an approximation. It definitely is wrong sometimes. But the overall characteristics of power in a large grid are sometimes still pretty well captured by this. And so for scheduling, say, generation in a big transmission system, it's often sometimes a lot easier to use DC power flow. It's not that bad to use AC either, so people have to do that sometimes. But this is sort of, it has a solution, all these sort of nice properties about it. OK, so having said that, maybe that's a good segue, even though we won't talk about DC optimal power flow, to transition now to optimal power flow. And the basic idea here is that in power flow, we assumed that all the powers were given to us. Well, all of them except the slack bus, right? Those were all fixed quantities. And we just want to ask the question, if we assume generators generate this much power, and there's this much power in loads, what will happen? That's the power flow problem. The optimal power flow problem says, well, if we don't know how much power different generators should generate, how much should they generate to satisfy power flow? Let's sort of forget about the slack bus doing whatever it takes to make up for the rest. Let's actually prescribe some cost to each generator, say the actual monetary cost it takes them to generate some amount of power. And let's just find what the optimal scheduling for all the generators is to achieve, say, whatever load we need in the loads. You don't want to, so what it really boils down to is that in power flow, 2n of these variables were fixed. And so it was just really a solution to equations. I mean, it was nonlinear equations, so it was nasty, but some solution to equations. In optimal power flow, less than 2n are fixed. You might have some additional p's, for example, that are free. Maybe even have some quantity like some nodes can adjust their demand or something like that too. So essentially, some more of these things are unknown. And because of that, you need some way of picking the best of them, right? For, say, 2n plus 2 unknowns and 2 equations, power flow, you can't find an optimal solution, or if you can't find a single solution. So we need to pick, in some sense, which z is the best according to some metric in order to achieve our objective while still satisfying power flow. I'll write this a little bit more formally in a second, but that's just sort of the basic intuition there. And so optimal power flow, or OPF, really it refers to any optimization problem that you solve where you're optimizing over some function of these guys, variables here, subject to a power flow constraint. So it's an optimization problem which has as one of its constraints a power flow constraint. That's what optimal power flow is. Sometimes people will actually use very specific cases of OPF, like they'll use it in the context of power markets, and that's what they'll mean, that specific version of OPF. But in general, it can mean really any optimization problem where you have a power flow constraint. Yeah?
Is the dynamic of the grid such that you can have like a general way of approaching this? Like the transmission lines all have very similar behavior. There's not much difference in material, stuff like that?
No, but that's all captured by Y. Sorry, I missed a bar here.
Oh, so it's not generic, but you do capture it in the variables?
Yeah. I mean, so going back to these examples, right? The reactances and resistances of all these lines are very different, okay. but it's known.
Right.
So power flow is what takes care of all that.
Okay. And that would be known from past history of like watching how.
That's typically known from physical characteristics. I mean, you also can estimate it pretty easily just from physical laws. If you know the power injection or you know the voltage at two sides, you can pretty easily figure and know the current flowing through. Okay. You can back out what the properties of the line are. But it also can just be known, say, from the materials of the line itself. You can estimate those things.
And then you'd approximate the distance of the phone.
Yeah, something like that. OK, so here is a fairly general formulation of power flow. And it's exactly what I wrote before. Essentially, you want to minimize over z. So z is our set of all variables here. So we're going to, at least initially, treat these all as optimization variables. Now, some of them will be implicitly fixed by certain constraints. But we're going to treat all of these in our general formulation as being optimization variables. So we minimize over z, subject to he of z equals 0, and hi of z is less than or equal to 0. And the e and I subscripts here refer to equality or inequality constraints. And these are sort of a general set of constraints that really can be anything you want. For example, a common one will be, well, at a load node, the pi for that load is fixed. And maybe the qi is also fixed for that. So you'd have an equality constraint that just said pn equals 2, or whatever your unit of power is in your MVA scaling. Similarly, there may be some inequality constraints you might have, like, for example, the flow over a line, the current flow, or current flow scaled however you want, over a line can't exceed some certain quantity. That would be an example of an inequality, right? Because maybe if you have too much current flowing over a line, there's a danger of it melting or something like that. That would be an example of an inequality constraint that you have to satisfy for these equations to hold. And then finally, the constraint, and those first two, I mean, I'm writing them very arbitrarily here because they can kind of be arbitrary. Maybe you don't have that many current constraints, and maybe some lines don't have them. Maybe some you just don't worry about them. Maybe some equality constraints are fixed, some ones aren't fixed. I mean, some variables are fixed by equality constraints, some ones aren't. But then you have finally this last one, which is just saying that S equals this thing, which is the power flow constraints. That is a constraint that you always have there. So that essentially is a constrains, that puts a constraint, an effective constraint on 2n of the variables here. The other ones might constrain other ones as well. And so essentially you have to then pick the rest that you have freedom over to minimize that objective f of z. And note that in power flow, we have to specify fewer of these variables than we did, in optimal power flow, we have to specify fewer of these variables than we did in power flow. Otherwise, there would be too many constraints and not enough equations. We wouldn't be able to, too many equations, not enough variables, and we wouldn't be able to solve them. So usually the way to think of this is, unlike in power flow, you know 2n of these. In optimal power flow, you know less than that. Say 2n minus 5 or something like that. Maybe just n of them. And you use the optimization objective to help you determine what the other ones are. Now, of course, the precise form of this problem can be very different depending on the setting. You might have different kinds of constraints, different kinds of equality constraints, different objectives, and different inequality constraints. But that's sort of a generic form that captures really any optimal power flow problem. Any sort of static optimal power flow problem. You can also have ones where you have multiple things over time, but we're not going to talk about that yet. That's for the next unit in the course. Now, in theory, at least, this is just an optimization problem, right? So you could solve it just with YALMIP. YALMIP, if you type in a nonlinear constraint, this constraint is nonlinear, but it will accept it. It'll do its best. And it, more likely than not, will not work. You type that into YALMIP, just as it is. And that's just because this kind of constraint here, this is a nonlinear equality constraint. And they're pretty tough to actually deal with in some sense. That's actually kind of hard. It's a non-convex constraint because it's a nonlinear equality constraint. And off-the-shelf solvers typically have a pretty hard time with these. Not all of them. There are some that can handle it fine. But YALMIP, with the solvers that you're using at least, it won't do very well. You type it in and it would say something like, can't find a, terminated without finding a solution or something like that. So the one case that I want to talk about is a simple case where a simple method for solving these kind of problems. In the case, for example, where the problem, say, would be convex. So this problem, for example, assume that it would be convex if only we didn't have this last constraint here. So, I mean, again, in this general formulation, all these things can also be non-convex. Right? We can have essentially, hi could be non-convex. That would make the problem hard. H of e could be nonlinear. That would also introduce nonlinear constraint. But assume for the time being that the only nonlinear constraint we have, or non-convex constraint we have, is this one here. So if we removed it, basically e is linear, and h of e is linear, or they're affine really. Hi is convex, and so this problem would be easy to solve if only we didn't have this one thing here. And in that case, which is actually not that hard to imagine, because a lot of constraints, like equality constraints, like certain constraints on current flows, can be represented convexly using all these things. And it's just this power flow constraint that makes things nasty. So in that case, I'm going to show you a basic way to solve these problems. It's called sequential quadratic programming, or I guess if everything's sequential convex programming, I guess in the general case. But basically what you do is you take your problem just as it is, and you leave all the constraints the same. You just linearize this constraint around some operating point. You resolve the optimization problem, and then you relinearize this constraint around the new the new solution you get out of that. And so intuitively, this is actually a lot like Newton's method, where Newton's method you have some sort of some candidate solution. You remember what Newton's method really is doing is kind of linearizing that solution around, linearizing that nonlinear. So I'll just draw a picture here to make it a little easier. What Newton's method was doing intuitively, remember from our little cartoon before, is you have it's finding a root of this function, right? So you have some function. And what you do is you linearize around this point, which what that means is you essentially approximate this function here by the gradient, the Jacobian at that point, that has the same slope as the function at that point. That's I did a horrible job of drawing that, huh? Something like that. That's supposed to be tangent there. Yeah, it's a pretty bad drawing. And then you approximated the function as a linear function that passed through that point that had the same slope as the function at that point, right? What we're going to do here is the exact same thing. We're going to take this non-convex equality constraint, the nonlinear one, And we're going to approximate it as a linear constraint around some initial point. So let me sort of write what I actually mean by that. So we have, now I'll erase this again here. But suppose that we have some sort of initial guess to a solution, Z0, for our optimal power flow problem. And you start off with just some sort of educated guess from the very beginning. It doesn't have to be that specific. But you start off with some initial guess. Then you form the Jacobian of our power flow problem. So the Jacobian with the Z of G evaluated at that candidate point there. And what this is doing, remember, is it's if you get this thing, then the linear approximation to G would be to say that essentially G of Z is approximately equal to G of Z0 plus the Jacobian of Z minus Z0. Is that the right signs right there? Yes. All right, so this is our sort of linear approximation given that Jacobian, right? This is a linear approximation to this function. And we want to set this to be equal to 0. This thing we can't directly set to be equal to 0 because it's a nonlinear function of G. But this thing is a linear function of G. Right? Because it has this Z0 term is the only one that sort of enters into it nonlinearly through this function G. So we're going to add the constraint that this thing equals 0. This is a little bit tricky. This is everyone sort of following because it's a little bit subtle what we're doing here. We're taking our power flow objective. We're taking some initial point, and we're linearizing our power flow function around that point. Now we can't set. And by the way, if we just set this to be equal to 0 and solve the Z that did this, that would exactly give us the. That is exactly just Newton's method. Right? So if this was the size of Z, if J was n by n and Z was in Rn, then the only thing that would satisfy this equation would just be the Newton update, right? This would be so if J of Z0 minus Z minus Z0 equals negative G Z0, then you multiply by J inverse, and what you get is you get that Z minus Z0 equals negative J inverse G of Z0. So in other words, Z equals Z0 minus J inverse G of Z0. This is exactly Newton's method. Okay? What we're doing here is we're just not, in our case what we have here, Z now, remember, is going to actually be bigger dimensional. So there are many things that can actually satisfy this thing. We can't just solve it like we do here. So what we do instead is we take this original form here and we just add it as a constraint in our optimization problem. This becomes a constraint, and it becomes a linear constraint on Z. And it is sort of the best approximation around this initial point Z0 to that power flow constraint. So the procedure is really simple, actually. It's very much like Newton's method. It's just except that for an inverse step, instead of an inverse step, we have a step where we actually solve the original optimization problem. So we first compute the Jacobian, and instead of just inverting it to find the next Z, what we do is we actually solve an optimization problem, where we actually solve this, we minimize over f of G, subject to all the constraints we had before. These are all convex objective and convex constraints we're going to assume, plus this additional linear constraint here, which is fine. That's still convex. We can still add it. And we get some solution to this problem. And then we just update our initial guess to be this new solution. Okay, we repeat that process. It's just like Newton's method. It's just that instead of inverse, because that's the one thing that solves that set of equations here, we solve an optimization problem given all these constraints here. So that's a little bit, it's a simple idea, but it's a little bit subtle what's really happening there. So Don't worry if it's a little bit confusing at first. You will implement it on the homework in the advanced version, I think. But I think everyone here is now doing the advanced class, so you will implement it. And essentially, what it effectively does something very similar to Newton's method, where you are solving different problems that at each iteration are closer and closer to sort of the Jacobian, you're solving different problems where if this thing is actually 0, and z equals z0, so sorry, if z star equals z0, then this thing is equal to 0. So if you solve it and there isn't any update to z, then you are at a point that satisfies power flow and solves, and optimizes this optimization problem. So you've effectively solved the problem. Now again, like Newton's method here, this thing can actually get you to not always the optimal solution. You can, depending on where you start, you can find some optimal solutions that you will converge to, but we won't worry about that this class at least. So here's a simple example, and maybe this will hopefully make things a little bit clearer in terms of what we're actually, how this differs from power flow. I'll leave this up here for now. So this is now showing an optimal power flow problem where, again, what we know is drawn here. So just like before, we have a slack bus, which we're going to assume has 1 pu of voltage at 0, at a voltage angle of 0. We'll have the same load as before. The load we know. We're going to assume we can't adjust the load. Some new sort of domains now, people assume that you can't adjust loads to a certain degree, things like demand response, but we're not going to worry about that yet. So we know the load here. The only difference between this case and the power flow case, for this simple sort of 3-bus example, is that we don't suppose that we know the power at the PV generator. So in our original power flow case, we actually said that we're going to fix this power. Then there are, in this case, 6 equations, 6 unknowns, and we just solve for them. Here, we don't suppose we know that power. We're just going to assume that the voltage magnitude is 1. You could actually also not assume you don't know the voltage magnitude either and solve for that also. But you typically want to constrain that to be a good amount, because if you start varying the voltage angle, or so the voltage magnitude too much, things get kind of crazy. So we won't do, fix it at magnitude 1 also. But we don't fix how much power it is. Does everyone remember this? This is exactly the same as this thing here. Before we said P equals 0.5, and that's the real power generator equals 0.5, and here we don't say that. Here we want to say instead, oops, I'm going too far. Man, I hit the wrong button there. What we want to say instead here is that there is some cost function that describes these generators. And we want to pick the generation schedule at the slack and the PV generator that somehow optimizes this. So what we'll assume here, and this is a pretty simple function, we'll assume that the cost of power, well, the cost really of all the variables, but we'll assume it just depends on power, the real power, is going to be the power at node 1, that's the slack generator squared, plus 2 times the power of node 1, plus 2 times the power at node 2, plus power at node 2. And what this looks like here is that essentially, I'll draw without axes here because otherwise I'll almost certainly screw them up. Essentially what it is that these both, in the imaginary world at least, have 0 cost if you produce no power. P1 though has a higher linear term and a lower squared term. So what it does is it sort of initially increases quickly, but then sort of as it gets bigger increases like that. P2 has a lower linear term, but a higher squared term. So at first, it's cheaper to generate power from generator P2, but then it starts getting more expensive. So at a certain point, power at P2 becomes more expensive than power at P1. So this sort of captures the fact that maybe they're different types of generation, they essentially have different cost functions. And so the goal of optimal power flow in this case is, given that we need to supply this much power, as well as satisfy power flow and not have satisfy the losses essentially in the lines, how much power should each of these generate to produce this much power to satisfy the load? And if you just solve that problem, essentially you take start with some solution, say they all just generate the amount of power, the voltage is equal for all of them or something like that. The same way you do power flow. Start with some solution, linearize the equation, solve the optimization problem, take out solution, relinearize around that new solution, repeat this process, you will get a convergence to this point. And so this actually prescribes now the amount of power that each generator has to generate in order to actually satisfy this problem. So it has to generate 0.72 units of real power, and that's 0.095 units of real power. And that's the best way to satisfy this load here, taking into account everything, the losses involved in the lines, how much power is flowing over what directions. If you wanted to additionally add things like you couldn't have a certain amount of power flowing across the line, you could do stuff like that too. So this can account for all of that while finding the best allocation of power.
Professor, would you ever have the other, instead of going like that, like that as a curve, would it ever be like that? Where it actually speeds up and then it...
So you're saying, is there a cost function like this ever, where it does something like this?
Yeah.
It gets
like polar, or nuclear might cost less when you get them at optimal? Is that a thing?
Right. So yes, but they don't look quite like this usually. What's more common actually is for something to look kind of like this. So essentially, there is zero cost for how's best supposed to erase the other ones. You can have cost functions like this certainly, where essentially so this is the cost, and this is power. You could have something where you can generate nothing for pretty cheaply, right? But to generate even a little bit will cost you a whole lot of money. Essentially the same as generating a lot. So essentially, if you have it off, that's all fine. But if you want to generate even a little bit of power, you have something up here. And so you essentially have a discontinuous function that, this is an open thing, I think, that is 0 when you're generating actually 0. But as soon as you generate any bit of power, you'll start doing something like this. So it does typically still increase the cost with more power. You won't usually see this happen, because that would be pretty weird. You can, I guess, get things that, yes, they probably, this is not quite linear. It's a little bit more like this, where the sort of the incremental costs actually go down the more power you generate. But this is pretty well approximated actually by a linear curve in a lot of cases, just the more power. But you definitely have this effect here at the beginning, where the startup cost takes a lot out of you. What's nasty about this is now also a nonlinear or non-convex objective. So this is not a convex function of the nice thing about these other ones here was that they were convex functions. P squared plus 2p is a convex function, and so you can always find a solution essentially, assuming you linearize power flow. If you do this, then you actually have a non-convex function that is still hard to solve, even if you do linearize power flow. So this is what people do with, if you've seen things like unit commitment and integer programming, this is sort of comes up, because you can formulate this as an integer program, where essentially you have these integer constraints that are either on or off. And if they're on, then you have a linear curve. If they're off, then it's 0. But that's essentially how you solve problems like that.
But if they're committed, can they be 0?
Yes, I think so. I mean, that sort of essentially corresponds to just wasting. I mean, it could be, but it'll never have that as a solution. Like, if you chose to turn it on, in the actual optimal solution, right? If you chose to turn the generator on, there would be 0 value to turning on and generating 0 power, because that would essentially be, I mean, I can give you another solution that's just as good, that generates the same amount of power, that has a better cost, namely just turn that one off. So if you turn it on, you typically have to have in the solution some amount of power being generated.
So if you ever chose to have that solution at 0, and that shows a sort of failure with the previous unit commitment optimization. Because then you wouldn't choose that unit in the first place, right?
If you ever commit to having a unit on and say it's on but generates 0 power, that is a suboptimal. That is not an optimal solution.
Okay. Thank you.
We'll deal only with convexity here. We won't deal with the non-convex cases. And just like, so it isn't quite as good as Newton's method, but it still converges pretty quickly. This is a plot of, I'm not quite showing, what I'm actually showing here is a difference between consecutive solutions, right? Because if this difference is 0, then we know that's what I showed before. That if the difference is 0, then we know we found an optimal point, right? Because then, that point doesn't add anything, so it satisfies power flow. I don't want to just plot g of z here, because what could be happening is that we have a point that satisfies power flow, but it's not an optimal point. So actually, what I'm plotting here is actually, in this case, probably both would look kind of similar, but in this case, what I'm plotting actually is the difference between consecutive solutions. Each one, by definition, is an optimal solution to its own problem. The question is, does it satisfy power flow? So we'll just plot that. You can also actually plot g of the current iterate, not any iterate, but the current one that is an optimal solution. That would be fine too, but I'm just showing it in terms of the difference there. And it actually gets what's called linear convergence here. There is not quadratic convergence, so this looks like a straight line going down, not like a thing that curves down. So I guess the number of correct decimal places increases by a fixed constant every time, rather than doubling every time. But we don't have to worry for this course about the precise nature of convergence here. Okay, so this concludes the little bit on just solving the optimization problem of optimal power flow. But I'm going to talk now about how this is used sometimes, and it's really an incredibly brief introduction to markets without talking about any of the actual complexities involved. But it's good to know kind of at least the cartoon picture of how power markets actually operate, because they are operating in practice. It's actually how we get our electricity. So are there any questions, though, about the optimization part of things? OK, so let's talk about power markets. And this, again, we're going to use optimal power flow here, but it's a slightly different topic. So I want to treat it as its own separate unit here. We might not quite get through it today, but then we'll finish it up with 15 minutes or so next time. And the question here is, how do we actually get our electricity? I guess fundamentally, right? If I turn on a light switch, there's a lot of generators producing that power. How do I know which one actually increases to give me power? Or even, actually, I guess that's sort of a, I shouldn't use that example, because actually that's sort of a separate process where the instantaneous changes like that. But if I'm need, just through forecasts or whatever, if I know I'm going to need, as a city, 2 gigawatts tomorrow, how do I know how to allocate that? How do I know how to schedule what generators to generate how much power, essentially? You have those curves for Pittsburgh, how much it's going to need tomorrow, some amount of gigawatts. How should I balance my generation to actually do that? And you can say, well, it's optimal power flow, but that's fine if everyone's cost is sort of true and known, right? If all generators are willing to sort of give their actual genuine cost, and by the way, none of them want to make money over anyone else, don't know how realistic that is. You can solve it with optimal power flow then. And that's actually a reasonable way of doing it if there is a monopoly controlling all the generation, right? If it's one company that owns all the generation, they're going to just schedule it to cost as little as they can, right? But and this is sort of that first lecture I talked about this a little bit, in the 90s and 2000s, the electrical industry moved away from monopolies to competition at the generator side. So now there is actually a market for generation. Anyone can build it. Well, not anyone, but a lot of people could, if you want to. You can build a generator and actually generate power for the grid. And this is a separately owned entity that is not controlled by a single monopoly. So how does that work then? How do you know of all the, and I want to make money over all the other people generating power too. I want to do better than them. I don't want to tell them my costs either, because A, I might want to get more than my true costs. I certainly don't want to get just my true costs or I wouldn't make any money. And B, I don't want other people to know exactly how much it costs me to make electricity. I want that to keep I want to sort of do my own sort of secret stuff. So with competition, even just in generation, it becomes a lot more difficult than it was before, because we need a way of knowing how to schedule different generators to actually provide for the power that we're going to need. And that's what that's sort of where power markets come into play. However, there is importantly some very big differences between traditional markets and power markets. And I think these are on the next slide. Actually, maybe I'll just sort of highlight them here. I have a slide describing them in more detail in a second. But essentially, a normal market will work basically saying that, okay, if I'm a producer, I can just put a new item on the market. Maybe it won't get picked up right away, but if it's cheaper than everyone else's and just as good, eventually over time people will start to use mine instead of other people's. You can't quite do that with power, because A, I don't want to really negotiate with all the different generators to try to find the best price, and B, there isn't really time for the market to settle according to normal kind of bidding and auctioning processes. When I turn on a light switch, I want power right away. I don't want to kind of go through a bidding process. Well, how much does it cost here? How much does it cost there? Before my light comes on. So power is sort of a fundamentally different different type of market than traditional markets, and we'll talk about some of that now. And where a lot of this comes from is what's called the theory of the firm. It's sort of basic microeconomics, but essentially, So some simple equations here, and this is really, I'm writing this mainly because I want to highlight how this differs from power markets. But for a normal firm, you have some cost and some amount of production. This is how much it costs you to make this many items. And typically, again, there might be effects where this actually does go the other way, but that's actually kind of uncommon. It might be like a linear function at best. But usually, at the scale we're talking about here, something like where it costs you a certain amount to make a certain amount of product. If you want to make more than that, you have to hire more people, or you have to do more things, or build bigger factories, so it will cost you more. Actually, don't forget about build bigger factories. That's sort of a longer term thing. But essentially, costs look like this, right? Where you have the cost that it takes you to make all these things and your quantity, and it looks like some sort of increasing function like this, right? What a firm will actually do is it will maximize, essentially, it will, in order to pick how many items to make, widgets are always the thing that economists use in their books, so determine how many widgets to make, you will solve this problem. You will maximize the number of things you make, where pi is the price, the market price of how much you're going to get from them, and c is your cost to make them. Okay, so you're going to maximize over y. Y is the number of things you're making. Pi of y, that's the price per item times the number of items you make. Yeah, that's what you want to maximize. Minus the cost that it costs you to make those things. And the point of all of this, by the way, is just to say, okay, when we solve this problem, well, the way we solve it is we differentiate with respect to y. So that says that pi minus the derivative of c of y dy equals 0. Right? We differentiate this to equal to 0. That's how we solve a simple 1D problem like this. And that just says, by the way, the sort of basic fact that the price, you make items up until the point that the price equals this quantity, the derivative of the cost with respect to the number of things you make. And so what you can think of this is the cost to make one more item at the point that you're making them, right? It's the incremental cost to make one more. And sort of one of the basic laws of economics here is that you make these things until your incremental cost equals the market price. So this is called the marginal price, and you keep making more because it's the price for making one more thing, and you keep making more until the price to make one more equals the market price. That's sort of very intuitive, right? At that point, you won't get any more from your money, so you stop making them. If it costs you more to make an item than what you'll get for it, you're going to stop making them, and you'll make it up until that point. Now, Okay, I guess I said that here. So the basic thing is, have a market price, keep making them until that point. Now, traditionally, the market price is actually settled kind of by the market. Yeah, question.
In this case, are we maximizing the generation? Why is the generation power generation?
Right. So I'm just talking kind of in basic terms here. It's a little different for power for the reasons I'm going to describe in a second.
What's the profit? Why?
Yeah, so if this is power, this is kind of a weird thing because power is not something where you can keep just making more. There's a fixed demand. So it's a little different, which is the things I'll get to in a second, why this is different. This is a traditional market where if it was power, imagine a land where you could just make more power and they would always buy it. Someone would always buy your power at a fixed price, whatever it was. So you would keep making power until the cost of power equals sort of what you get. The incremental cost of power, which is the derivative of your cost of power, equals whatever someone's paying you for it. But don't think it's generation, because that's actually kind of a different situation. That's sort of the point of all this, is that power markets are different than traditional markets like this. In a couple ways. First of all, again, the traditional way a market works is that this price is set by kind of an interaction of supply and demand. So if there's lots more of a quantity, then people will not want to pay as much for it. That increases the price. If there's not much of it, they'll increase the price. That's not really, I guess maybe long term that could be kind of how power works, but it's not really how it works right now. I don't think about like what's the cost of power right now when I turn on a light or not. I just turn it on. Maybe this is actually a problem in the big scheme of things that people don't think of power like this. But there are a lot of idiosyncrasies to power markets that make this a lot tougher. First of all, I kind of mentioned this beforehand, is that we need to respond instantly to changes in demand. There isn't really time for the demand and supply to kind of together settle to a certain market price. We're going to assume that demand is fixed. It's not that we have a certain price out there. It's that the actual demand, the number of things, not that we're going to make, but that the world as a whole wants, is fixed. Unlike most markets, if you can't sell your widgets today, it's okay because you can just put them in a truck and sell them tomorrow, or a big warehouse sell them tomorrow. You can't do that with power. If you don't use it when it's generated, it's not going to be used later. Maybe eventually we'll have storage that can account for this problem, but right now at least we can't yet store grid level amounts of power. I guess people are actively working on that as we speak, but can't do it quite yet. As I said before, demand is viewed as fixed. We don't want to think about, with some caveats for things like demand response, where we actually can adjust demand. In general, whatever the power grid requests, we want to provide for. And the generators, it isn't like there's a fixed price and they turn up at that price, but it really is there's a fixed demand and they generate up to that demand. And finally, the distribution of power still has to obey these power flow laws, right? You can't, if I have a bunch of power over here and I have a bunch of power over here and I don't have a transmission line with enough capacity in between them, I can't get it over there. It doesn't matter that I can generate as much power as I want over at point A if I can't get it to point B. So all these cause significant differences between traditional markets and the power market. Trying to decide.
You view these in the context as as constraints to the optimization?
They're more this is not just an optimization problem at this point. This is more like a design of a market system. So these are constraints to the design of a system that could actually be anything like a feasible market for power.
So they were trying to think about how to deregulate the market and make a market.
Yes.
This is what they did.
Right. When they were thinking about, how do we go from these monopolies that each control their own thing, they're going to make the best decisions, to a situation where independent companies can participate in a generation market, this is what they think about. Because these are all constraints that make us different than just saying, okay, let's open it up like any other market. It's easy. So these are sort of the things that came up. So let me talk about now quickly how this works. And again, this is a very cartoon level. It actually happens at different time periods. There's a lot more going on here, but this is how one type of market works. And it is, though, how it works. This is really what's going on, the way we get power. So the big problem, I think, with a lot of these things is that unlike a normal market, a completely kind of free system doesn't really appear to work here, right? It's not like we can just have a bunch of generators all hooked up together, they are doing whatever they want, and then the consumer's doing whatever they want. Because if they don't have enough power, who's responsible, really? Like, what's going on there? We really don't want to have things like lots of blackouts, or so it seems somehow fundamentally more than just a matter of cost. We expect this, at least in this country. So here's how it works. It works with something called an independent system operator, or a RTO. What does RTO stand for? What does RTO stand for again? Regional transmission operator, yeah. So the ISO or RTO, which are essentially, there are technical differences, but they're essentially the same thing for the most part. A lot of RTOs call themselves ISOs and vice versa. But essentially, there is a central market maker in electric markets. And you need this because it has to happen very, very quickly, and it has to be kind of guaranteed. So what happens is that, say, at different time intervals, so this happens a day ahead of when you actually need it, but it also happens maybe 15 or 5 minutes ahead of when you actually need it, or an hour ahead. What happens is that the loads, all the things that are going to consume power, which, again, we're not talking about light bulbs, individual light bulbs, we're talking about substations now, because we're talking about at the transmission grid level. So all the substations report how much power they're going to need. And they do this by forecasting, by whatever. I mean, the closer you are to the time period, the more accurately you can forecast. But we were doing pretty good forecasting with some simple predictions, so it works pretty well. And so the loads all tell the operator, this ISO, central market maker, how much they're going to need. Then the generators all report to the ISO how much it costs them to make power. So this is sort of the key thing, is that we wanted this sort of central market maker so we could solve a single optimal power flow problem, but we don't want these generators to have to tell each other what their cost is. So we create a single entity that is bound not to let certain ones cheat over other ones and bound not to tell anyone. We all take our generators and we report them. We report our how much it'll cost, not the generation number itself, but our cost curves. We send these to the ISO. The generators do. Send their cost curves themselves to the ISO. Now these could or could not be the real cost curves for them. I mean, a lot of research actually deals with how do you ensure that they are giving accurate representations of their costs. But if they report something wildly high to try to make a lot of money, then barring any weird circumstances, they'll probably not get picked to generate the electricity by the ISO. So loads report their demand. Generators report their actual functions. They report their cost curves. The ISO then solves the optimal power flow problem, which in this case, essentially, usually, is minimize the cost of generation subject to everyone getting their desired load and power flow constraints being satisfied. That specifies an allocation of power. Then the generators go ahead and turn on their desired amounts, and because the computations are all correct, when you do that, everyone gets the power they want while satisfying all the constraints. Now, of course, there's some errors there, and you can make up with errors in other little ways, but for the most part, this is how kind of the large amounts of power are allocated. Yeah?
Does FERC give them certain restraints to how they're able to come up with their cost function? Or are they just free to, game theory?
So I mean, there's a certain format to a cost function. They basically give it in sort of linear increments in terms of the derivatives here. But they are welcome. I mean, I think they are, to a certain extent, free to kind of do game theory stuff if they want to. There are other markets where you cannot do that, where you have to basically guarantee that you're going to provide a certain amount of power. And here, actually, if you make a bid, you have to live up to that, and there are big consequences if you don't live up to that. But that's more what it's about, not about sort of how to play the game here. People, the idea being this is the market, right? This is sort of the power of the market, and you want to let that happen as much as possible. The bigger stuff comes up in things like, boy, there's a ton of other things that come up quickly, and I'll mention them at the end. But things like transmission, all this kind of stuff is much trickier to handle here, and there are more regulations there, or there are other kinds of markets there. But I believe that they are, for the most part, I mean, they're allowed to certainly play some games. Maybe they can't. Maybe they're restricted in sort of how much they can play. And I think that if there is a blackout, for example, and a certain place is the only power source for a place, they can't just raise the price to do whatever they want, probably. There are probably some restrictions, but on the margins, they can play these games to try to make more money.
Okay, thank you.
right, I'm gonna stop it now, but I guess we're over time, so I'll just stop. But if people have questions, they can stay afterwards and ask.